So now I turn on the live on SPICE now. So we will be going in a few minutes. It's typically there's about 20 to 30 seconds delay.
Should I already share the screen or not yet?
No, it's fine. I usually cut. I will be sharing first the screen. So I usually cut things. Let me turn off my Skype. Spotify,
yeah, this is so.
I'm just turning off everything that is unnecessary at the moment. Right. Like that one. And I have your, yeah, I'll share my screen in a minute, in 2 minutes or so. Oh. I guess there's not a... Where did you do your PhD? I think Elena didn't write it down here.
Where?
Yeah.
In Dresden.
In Dresden as well, okay. But
Yeah.
there's education there as well.
Mm-hmm.
So I'm going to share the screen real quick. Let me see if Martin is here. Hang on a second, Martin. Let me promote Martin, two panelists, board card prepare. Really plans.
Martin Eschlimann.
Yeah, so he's a co-organizer.
Yes, I know.
Our
Guten Tag.
Guten Tag. He's the Swiss of our guys, yeah.
Thanks for the. Okay.
Okay. Let's see. I think I'm sharing, but I don't know why it's not showing up on the live. Okay. Oh, I see. Very good. Let's see. Put this here in the stream. The Q&A. Hey, great, long time no see. Igor Mastin says hi. He says, and I sit well. Let me see if Burkhard is here. Yeah, let me promote Burkhard real quick. So Burkhard is another co-organizer of the and co-speaker of the group. Matthias Klaue, unfortunately, is still on vacation.
He sent me an email.
Who?
Matthias.
Well, he's always busy, but I don't think he knows what a vacation looks like.
Hallo Burkhard.
Hallo Ingrid. Schön, dich mal kurz begrüßen.
Nice to see you.
Tito. Ja.
Okay.
Ich weiß nicht, ob ich ganz bis Ende dabei sein kann, aber schauen wir mal.
Kein Problem.
Gut. Where's that?
Aber am Ende kommen die neuen Sachen.
Das ist immer gemein. Kann man das Ganze nicht auf Anfang bringen. Ja, so ist das halt. Ich weiß.
Okay, so I think I'm pretty close to there. I think I should start. So let me go ahead and start the meeting. So thank you very much, everybody, to come once again to the SPICE-SPIN+X seminars. These are a seminar series organized by the Spin Phenomenon Interdisciplinary Center, that led by myself, Jairo Sinova, Karen Evershaw-Sitte, the scientific coordinator, and Elena Hilp as organizer of many events. And it's to co-organize with the SPIN+X, the Collaborative Research Center, where the speakers are Martin Eschlimann, Burkhard Hillebrands, and Matthias Klaue. Just to be clear, this is a webinar format, so the attendees will only be seeing the video and whoever is speaking at the time. And please write your questions in the Q&A with your name. Please don't do it anonymously, because then afterwards I will pass on the allowed you to use the speaker to ask the questions directly and converse directly with the speaker, with Ingrid Mertig today. Just please be polite. If not, unfortunately, I will have to kick you out of it, but that's not really been the case at any time. And please check out the next speakers, which happens to be, we're very proud of. The next week will be Burkhard Hillebrands to tell many things about the magnonics, quantum magnonics, that he's pioneered over the years. Just a couple of words about Ingrid. Ingrid Mertig is a full professor at Martin Luther University in Halle. And she graduated from Halle and did her habilitation in 1995, was a postdoc for some years in Russia. But he's really well known in our field from ab initio studies of transport and theory of magnetism and spintronics. Has quite a few awards and is very active in the field, and in particular in spin Hall effect physics, something that is close and near to my heart. So with this, I will stop now sharing, and I will ask Ingrid if you want to go ahead and share your screen.
Yes.
And I will stop sharing my screen, and I will only interrupt if there is any sort of a need at some point, okay?
Okay, thank you. So, thank you very much for the kind introduction and for the opportunity to talk in this nice webinar. So, my talk is on topological properties and Hall effects. And after a very general introduction, I will talk about topological Hall effect in particular. Then I will give some insight into the anomalous Hall effect for coplanar antiferromagnets. And finally, I would like to discuss the magnetic spin Hall effect and the relation to spin current vorticity. So I start in general with transversal transport coefficients, which are known as Hall or Nernst effects. And it started with Edwin Hall discovery in 1879, where he found out that there is a transversal voltage if I apply, if I have a system with an external magnetic field and a current. And this transversal voltage is due to the Lorentz force and is the standard Hall effect, which separates the charge carriers by charge. A short period later, Hall himself discovered the anomalous Hall effect. Now, instead of the external magnetic field, he considered a system, a ferromagnet, with an internal magnetization. And we know that for a ferromagnet, the number of electrons with spin up and spin down is different. In this effect, so the electrons are also separated in transversal direction, but not separated by charge, but by spin. And since the number of spin up and spin down electrons is different in a ferromagnet, we also observe a voltage, a Hall voltage. In 2004, the spin Hall effect was predicted and also discovered. And now, if we go from the anomalous Hall effect to the spin Hall effect, we have the following difference. This was a ferromagnet. For the spin Hall effect, we just use a metal. And we don't have any more magnetization. And the number of spin up and spin down electrons in a metal is the same at the Fermi level. So all states, all bands are degenerate. And we have also a transversal selection of electrons with spin up and spin down to different edges, but we don't have a voltage, since the number of spin up and spin down electrons is the same. So there is no direct way to measure the spin Hall effect, since we don't have terminals to attach to measure the spin accumulation, but we can measure it by inversion, the so-called inverse spin Hall effect, and then we get the voltage. So it took a long time until the two effects, the Anomalous Hall effect and the spin Hall effect, have been explained theoretically. And it's so that both effects are related to spin-orbit interaction. And another way of explaining it, they are related to a topological property in the system, and this is the Berry curvature. Now, let me come to the semi-classical equations of motion. So everybody knows the Lorentz force. It's a change of momentum by an electric field and by an external magnetic field. So we know that the Lorentz force gives rise to this transversal component in the conductivity. And there is another semi-classical equation of motion, as is change of position, which is the derivative of the dispersion relation by K, which is the Ehrenfest relation. And it's the velocity, the group velocity of the electrons. And since 1996, we know that there is another term which is related to the Berry curvature and can also give rise to a transversal component in the velocity, the so-called anomalous velocity. And so the Lorentz force and the anomalous velocity are responsible for this non-diagonal elements of the conductivity tensor in case we apply an electric field. Of course, all the non-diagonal elements could be non-zero in principle, but for simplicity, I concentrate to a cubic or tetragonal system, and then I will have particularly these two elements. So now, if I want to calculate them by means of the electronic structure of the system, and I have several contributions. I have so-called extrinsic contributions, which are related to scattering in the system, as this is usually the case for transport. But there is also an intrinsic contribution, and this is the contribution I will concentrate on in my talk, which is related to the Berry curvature. And I come to this intrinsic anomalous Hall conductivity. It can be calculated by the Berry curvature. This is here, this part, and it's an integral over the Fermi surface, and it's written down for a three-dimensional system, and it gives rise to non-zero, non-diagonal elements of the conductivity tensor. And here you see the Berry curvature expressed, calculated from the electronic properties of the system, which is the velocity. These are the velocities and the energies of the system under consideration. It's important that the bands I consider for the calculation of the Berry curvature, it's always the influence of all the other bands. The Berry curvature of band N is the influence of all other bands M to this band. This gives rise to this property. So now I would like to use it, and I would like to make another jump in my introduction. So if I calculate this property, I have to integrate over the Brillouin zone. And of course, I have to integrate over all occupied states, which you can see since I have the Fermi-Dirac distribution function in here. But in case I integrate over my band is fully occupied and my Fermi level is in a gap, and my system is a topological insulator, then I have just the edge states in the gap, and my conductivity, my anomalous Hall conductivity, is going to be quantized. Since this integral, if I do it over a full band, is going to be a topological invariant, the Chern number. It's called C. And if I consider this situation, that the Fermi level is situated in a gap where I have only edge states, then the anomalous Hall conductivity is going to be quantized, proportional to the Chern number. And I come from my 3 Hall effects that I introduced in the beginning to the quantized versions of the Hall effects. It's now the quantum Hall trio, if you want. So if I, and it's the same arrangement as before, if I apply an external magnetic field to a metal, then I have Lorentz force, and now the edge states are moving due to the influence of the Lorentz force along the edges, and they have opposite spin. But the charge of the edge state contributes to the conductivity. Then let me go to the next case. Now I have again a metal, and as before, no more external magnetic field, but still I have, because of Berry curvature or spin-orbit interaction, I have these edge states or edge electrons moving with opposite spin, moving in opposite direction. It's a difference here from here. The red and blue arrows are opposite here. And this means I have no charge current in this system, but a spin current. And then if I go from a metal to a ferromagnet, the spin degeneracy is lifted, and if I'm lucky, I have just one edge channel with a certain spin. Okay. This was my introduction, and I would like to show you now a new Hall effect, which is the so-called topological Hall effect. And I would like to show you how this effect is related to the ones that I presented before, that I discussed before. This goes back to some work that was done in collaboration with Birger Goebel, who was a PhD student at that time, with Alexander Moog, as well a PhD student in my group. He is now a postdoc in Basel in Switzerland, and with Jürgen Henk, a member of my group. And we did some work on this topological Hall effect. And I just want to start with an experiment that how to measure that. When would you observe that? How would you observe the topological Hall effect? So the topological Hall effect could be observed if you have a chiral spin texture in your system attached, for example, to a 2-dimensional electron gas. Then you apply an electric field, you have the Hall voltage, and you can observe a charge current and even a spin current in transversal direction. let me concentrate to the charge current in this situation. And the chiral spin texture I would like to discuss is a skyrmion lattice. This is a nice experimental observation of skyrmion lattice by the group of Tokura. And this is our view of a skyrmion lattice, very irregular, but with the same colors as in the figure before. Now we investigated motion of free electrons in such a spin texture of the skyrmion lattice. The spin texture, this is the spin texture of one unit cell. And this is the spin texture Mi, and we describe this by this simple Hamiltonian, which consists of a term that describes the motion of the electrons and a term that we call Hund's-Rule coupling term that couples the spin of the electrons to the spin texture. And let me consider the solution for the electronic band structure of such a system. So if my magnetic moments in the spin texture are zero, I have a large unit cell, very many sites in the unit cell, hexagonal unit cell, and I have a lot of degenerate bands due to the high number of atoms in the unit cell. If I switch on the spin texture, so I increase the length of my magnetic moments, then I see that I observe degeneracy, that the degeneracy is lifted. And I observe blue and red band, which indicate the orientation of the spins with respect to the orientation of the spins with respect to the texture. And there are also still gray bands with mixed orientation. So, but then if I increase the size of the magnetic moments, I end up at this case where the splitting is so large that I have two blocks, a lower block with magnetic moment of the electrons, with the spin of the electrons always oriented parallel to the magnetic moments of the texture. And there is an upper block with spin of the electron opposite to the spin texture. Okay, and I will, for simplicity, I will discuss this last case. And I will calculate the Hall conductivity for the lower block of bands that we have seen before. The upper block will give the same result, just with opposite sign. So for this reason, I concentrate to the lower block. What do I see? It's the formula that I presented before, but now for a two-dimensional case, since the system under consideration is two-dimensional. So what do I see? I see lots of bands, and in the conductivity, in the XY component of the conductivity as a function of energy, I see plateaus. There is one band, there is a plateau, and the height of the plateau is E squared over h. And the next band comes, and I see that there is a plateau which is 2E squared over h, and so on. The plateaus are not, since my bands show dispersion, the plateau is not so large, and all the deviations from the quantized value are the regular anomalous Hall effect, not the topological. Maybe I come back to this question again. And there is also another part of my band structure that gives rise to a jump to 2e squared over h. Now, how can I understand this behavior of the Hall, anomalous Hall conductivity for this fermion lattice? Let me now consider the same effect in the following manner. I have my spin texture of this fermion, which can be characterized by the fermion number. And the fermion number is the emergent field of the fermion, which is color-coded here below the fermion texture. And what we did, we homogenized the emergent field of our fermion in the unit cell under the condition that the topological properties are kept, or that the topological properties are conserved. Now, we take this emergent field, which is nothing but the Berry curvature in real space now, and go to another Hamiltonian, which is the Piles substitution. We go now to free electrons moving in this emergent field. The emergent field enters the Hamiltonian as a vector potential. What happens? Free electrons in this emergent field. Of course, we observe Landau quantization here. We have our hexagonal the free electrons in our hexagonal unit cell, and we observe Landau quantization. And we calculated the anomalous Hall conductivity. And it looks very similar to what was calculated before. We see the jumps which are proportional to e squared over h. And we also see a sign change at the Van Hove singularity. And we have then jumps by 2e squared over h. Now, how is this related to my anomalous Hall conductivity and to the Chern numbers that I discussed before? We also calculated the Chern numbers of the Landau levels. And what you see is that each Landau level has a Chern number -1 and gives rise to a step in my conductivity. So this means each Landau level, so we go over all the Landau levels, we reach the Van Hove singularity, and then we have the sign change, and then we have this Chern number of -2 for the other Landau levels. How is the -1 and the -2, how can we understand this difference? For the Landau levels above the Van Hove singularity, the electron orbit is a whole orbit, and we have just one in the unit cell. So this gives rise to the -1. Below the Van Hove singularity, we have electron orbits. So this is the sign change generally in the conductivity. And we have 2 electron orbits in the unit cell. So for this reason, we have the factor of 2. Now, let me compare this free electron gas in the emergent field with our result, the free electrons with their spins coupling to the spin texture. So the band structure is really very similar. We have a correspondence between the Landau levels and our bands. Of course, in our system, our bands have a dispersion. Here we considered free electrons and we do not have dispersion, but otherwise, so there is a one-to-one correspondence between the 2 band structures. So we have 2 ways to describe the system. either we describe free electrons coupling to the spin texture by their spin, or we describe the electrons moving in the emergent field. And this gives the same result. If we now compare the conductivity, we see, of course, what I said before. We have this curve that I discussed for the free electrons, and this is our curve, and they are very similar. Now, I would like to show you the band structure again, but this is now not the bulk band structure, but the surface band structure. What do I do for a surface band structure? The system is a two-dimensional system, so I have a two-dimensional Brillouin zone. And now what I do is I project the bands of the two-dimensional Brillouin zone to one edge, a certain edge, which is the surface. What I see is that my bands, since they have dispersion in the whole Brillouin zone, are going to be these blue areas. So the dispersion over the whole two-dimensional Brillouin zone is now projected onto the edge. And so I see what we have seen before, bands with dispersion, the Landau levels without dispersion, but in the surface band structure, I see the edge states. And I see now that each edge state gives rise to a jump in the conductivity, in the anomalous Hall conductivity. I have one edge state in red, and I have a jump by E square over H here and here. But then I would like to discuss this little dip. This is not a numerical error. This comes from the regular Hall effect, not from the quantized Hall effect, which is now, since I'm already in the band, I have this Hall effect, this anomalous Hall effect from the bulk band. And the direction is opposite to the quantized Hall effect, so it's a reduction of the quantized Hall effect. Okay, and you can count the bands for all gaps, but let's go back to these, the last here, where we had the jump over 2 E square over H, and you see 2 edge states in here. And all the edge states are attached to the Van Hove singularity, which is a certain band with this very high Chern number of 24 minus 1. Okay, so to summarize this part, I have shown you a new effect, the topological Hall effect, but on the same, I wanted to show you that the topological Hall effect is nothing but the quantum Hall effect. As the magnetic field, we use the emergent field that is created by the skyrmions. Or in other words, the topological Hall effect means that we have, it's also an anomalous Hall effect, with the difference that the electrons are not moving in a collinear ferromagnet, but in a chiral magnetic system. And the edge state, which has a well-oriented spin in this situation, in the quantum anomalous Hall effect, is now non-collinear. The edge state, the electron spin, when the electron is moving, the spin is turning. Okay, this is this new effect. Now let me come. Short summary, I have shown you all the different Hall effects, and I also discussed that the topological Hall effect can be mapped on the quantum Hall effect or can be understood as an anomalous Hall effect. Now I come to a new effect, the anomalous Hall effect in coplanar antiferromagnets. This goes back to some work that was done in collaboration with Oliver Bush in his master thesis and Berge Goebel, and it's just accepted for publication. And coplanar antiferromagnets are systems like the manganese-3 iridium, for example, is shown here. I have a unit cell with the triangular magnetic order. And in 111 direction, I have a certain stacking of Kagome planes with this triangular magnetic order. This is what I would like to discuss later on. I will concentrate to such Kagome planes. So this anomalous Hall effect in coplanar antiferromagnets, there are many publications, theory and experiment already on this. I only want to offer you some microscopic understanding of the effect. And so the effect occurs in two classes, the manganese-3 iridium that I have shown you before. This is an FCC lattice with this ABC stacking of the Kagome planes. And there is manganese-3 germanium, where we have ABA stacking of the Kagome planes. And this effect was predicted by JGU, Alan McDonald and collaborators in 2014, and Jürgen Kübler and Claudia Felser calculated large anomalous Hall effect in these systems, and very many papers followed. So why I was interested in this system from the beginning, since usually the anomalous Hall resistance is proportional to the magnetization. But now in these systems, the magnetization is 0. And I was always looking for an order parameter that could be important to understand this large effect. So let me consider the same Hamiltonian as before for the skyrmions. And this is the Hamiltonian that was also discussed by Alan McDonald's group. We have kinetic energy, the free electrons moving in a spin texture, in a non-collinear spin texture, which is now simpler than in the skyrmion. It's just this triangular texture that I would like that I will consider, and it's Hund's rule coupling. And nu is the third term, which is spin-orbit coupling. And this is related, so these little vectors n are seen here as red arrows in the system. And yeah, let me go back again. So the spin texture or the system has certain symmetries. The system has an effective time reversal symmetry. That means it's a combination of time reversal and mirror planes that is seen here. Now, we investigated this Hamiltonian and calculated the band structure and the anomalous Hall effect as before. Same formulas as before. It's also a two-dimensional system. Let's start with the band structure without spin-orbit interaction. So we see in the band structure certain crossings, and the bands are gray. That means we have no set component of the expectation value of the spins in this system along the bands. Now we switch on spin-orbit coupling, and we see that the crossings, we have avoided crossing, and we see that the character of spins changes along the bands from the set component, the expectation value of the set component of the spins changes from -1 to +1, so from changes direction. And we calculated the anomalous Hall conductivity as before, and we see a certain dependence For the case without spin-orbit coupling, we just see a black line. And the black line means the effect is 0. But with spin-orbit coupling, we see this curve. And this was calculated by many authors before. We just repeated the calculation and found the same result. I even want to say that within this gap, we even have quantized anomalous Hall effect since we have edge states in this gap. Okay, how can we understand this, that although the resulting magnetic moment is 0, we have such a big effect? Arita and his group tried to explain it by multiple moments, higher order moments than the magnetic moment. But I would like to offer you another way of understanding. So what we did then, we started from this coplanar texture and did some tilting out of plane. And this is the tilting angle theta. And at 90 degrees, I have the texture that I started with. And then at 0, I have a ferromagnet. At 180 degrees, also ferromagnetic order, but opposite direction. So what is interesting in this result? We have no effect without spin-orbit coupling, no effect for 90 degrees, which was my black line before, and no effect for ferromagnets. Without spin-orbit coupling, we won't have anomalous Hall effect. Now I switch on. So this was the particular point of interest. Now I switch on spin-orbit coupling and I compare the results. And the results look like, if we concentrate to one of the, so maybe I should mention one thing. So I mentioned that there are certain angles with 0 anomalous Hall conductivity, but of course, most of them are non-zero. I didn't say why. But this is clear that now we have an out-of-plane tilting, and it's more like a topological Hall effect, since the 3 spins have now an opening angle, and also I have a resulting magnetic moment, so that there is, I understand that there is a finite signal for all the other angles besides 0, 90, and 180 degrees. Now with spin-orbit coupling, if I compare, let's concentrate to the black curve. So all the different curves are for certain energies that I presented before in the energy dependence. Just the black curve. It looks like the black curve is shifted with respect to the same function, but shifted with respect to the angle. So this is this little shift that is indicated here. So you see that the special points where the anomalous Hall conductivity was 0 because of symmetry are now at different angles. And in particular, at 90 degrees, I have this large anomalous Hall effect that we want to understand. But at 103 degrees, the effect is again 0 for all energies, I have to admit. And there's also at 13 degrees, it's also again 0. Also, I have some canting. How can I understand that? So let's go to the band structures. Band structure for 0 degree, which is the ferromagnet with spin-orbit interaction. You see avoided crossings, and you see mixing of the out-of-plane direction of the spin expectation value. And if we go to 13 degrees, we see it's a different band structure. We have no more avoided crossings, we have crossings, and we have kind of a spin polarized band structure. and the same for 103 degree. We have two subsets of bands with a certain out-of-plane expectation value for the spin. So let me come back to the Hamiltonian again that we considered and to the coplanar spin texture. And the coplanar spin texture was 90 degree. It's just here. And now with spin orbit coupling, we have this large finite value. In the next step, I will transform my Hamiltonian by unitary transformation. It stays the same physics, but it's a different, the Hamiltonian changes. So after unitary transformation, I have different operators. I have some effective hopping, and in my Hund's rule coupling term, I have a different spin texture. We called it a virtual spin texture. The real spin texture was the 90 degree spin texture was coplanar. The virtual spin texture looks like tilted out of plane. And with this virtual spin texture, it's easy to understand that we have a finite anomalous Hall conductivity at 90 degree. Since the virtual spin texture has now an opening angle between the three magnetic moments, which gives rise to a topological Hall effect, a large topological Hall effect. And there's also a smaller contribution that we analyzed in detail, which is proportional to the out-of-plane moment of the magnetic moments. And this is a regular anomalous Hall effect. But this is in comparison to the topological Hall effect smaller. Now, there is also another change in after the unitary transformation, the spin orbit interaction also changes. I go over from lambda to a lambda tilde, and this is now an effective spin orbit coupling. And in particular, this lambda tilde can, for certain angles, alpha of my unitary transformation can become 0. And this is what happens here. At this angle of 103 degree, my Hamiltonian, after the unitary transformation, is going to be the same as my Hamiltonian before without spin orbit coupling. So what does it mean? How do I understand this? For 103 degree, my virtual spin texture is going to be coplanar. So, and as a consequence, so now the symmetry of my Hamiltonian is restored, and the anomalous Hall effect is forbidden and is going to be 0 for all energies, as was also calculated. So now, let me summarize this part. I wanted to present you a new view on the anomalous Hall effect for Kagome antiferromagnets, and I wanted to offer you a microscopic picture, namely that the anomalous Hall effect is caused by spin orbit interaction, leads to a virtual spin texture that is responsible for the Hall conductivity, instead of the spin texture that you would measure. This virtual spin texture gives rise to a topological Hall contribution, which is proportional to the opening angle and similar to what we have seen for the skyrmions. and also to an anomalous Hall effect, traditional one, which is proportional to the resulting out-of-plane moment. So I still have, I think, a few minutes, and I would like to go to a third part of my talk, the magnetic spin Hall effect and spin current vorticity. This work was done in collaboration with Robin Neumann, who is also a master student in my group, with Annika Johansson, Alexander Mork, and Jürgen Henk. So it's again, magnetic spin Hall effect is again an effect that was predicted by Jakub Żelazny and collaborators, and also was measured by Otani's group. And it's a similar aspect. I want to present, let's say again, a microscopic picture when the magnetic spin Hall effect will occur, a simple picture. Again, like the same as before, similar to what I discussed before. So this is published, just published in this year. And let me first compare the magnetic spin Hall effect with the anomalous Hall effect. And let's consider a cubic or tetragonal ferromagnet with the magnetization in Z direction, applied electric field. And the anomalous Hall effect is what we discussed until now. We will have a perpendicular motion of the electrons to left and right edges sorted by their spin. The magnetic spin Hall effect will have the same arrangement. I just turned the cube a little to make it more visible. It gives rise to a spin current. But the spin current would lead to spin accumulation at the surfaces which are perpendicular to the magnetization. So it's a pure spin current parallel to the magnetization. So which is, if you want to observe it, you would have the magnetic spin Hall effect at different surfaces than the anomalous Hall effect. So now I have to come back to the formulas to calculate this effect. So until now I discussed the conductivity tensor, and now I would like to discuss the spin conductivity tensor, which is a tensor of third order, and we have 27 elements. But under time reversal symmetry, we have an odd part of this tensor and an even part. And I have written them down in a similar way as before, my conductivity tensor for the anomalous Hall effect. The only difference is now that we have here not only the charge current, but also the spin current included as operator. Yeah. So the even part of the spin conductivity tensor gives rise to the spin Hall effect. The odd part gives rise to this new effect, the magnetic spin Hall effect. And if I want to illustrate this again with some cartoon. Now let's consider a ferromagnet, magnetization out of perpendicular to my screen, electric field also perpendicular to the screen. The spin Hall effect would give rise to a spin accumulation along the edges with spin direction indicated by the blue arrows. The magnetic, this is like a toroidal order. The magnetic spin Hall effect would give rise to a spin accumulation with spin direction in radial order. So the spin Hall effect is even under time reversal. This is if I change the direction of the magnetic moments, the tensor components stay the same. if I change the magnetization, if I change time reversal symmetry, I go to opposite magnetization, nothing changes for the spin Hall effect, but the magnetic spin Hall effect changes, the spins change their orientation. So, and now comes the idea. For each spin direction, we have we have three independent non-diagonal elements of the spin Hall conductivity. And these three, the antisymmetric part of the spin Hall conductivity for each spin direction separate can be arranged as a vector, the so-called magnetic spin Hall vector. So these are originally each gamma is a 3×3 tensor and has three independent non-diagonal elements, and they are now here. If you analyze, and you would get three vectors for gamma x, y, and z, spin orientation. If you analyze the coordinates of your components, you find out that you can write this vector as a cross product. Since you see this y, z, z, x, x, y. And it's a cross product between the spin conductivity, the spin current, and the charge current. And if you go to t equals 0, zero temperature, this is going to be a delta function, and the integral is a surface integral over the charge current is going to be the velocity, and this is my spin current density. And now if I go to this integral can be interpreted as a vorticity, a spin current vorticity. So everybody knows what a vorticity is. This is a nice word. And what we say is that I have now we have now calculated the spin current for a certain spin direction over the Fermi surface, and you see that there is a vorticity similar to the vorticity before. And what we say is that the magnetic spin Hall effect is non-zero if the spin current vorticity integrated over the Fermi surface is also non-zero. So we did, of course, Jakub Železný presented that already, and we also did an analysis of all the different Laue groups, magnetic Laue groups, which groups will give rise to a magnetic Hall effect. But I would like to summarize it in a simple way. First of all, so we need a non-zero integral over the spin current vorticity in the Fermi sea to get the effect. And this means this effect can occur in any ferromagnet. It can also occur in antiferromagnets with magnetic Laue groups that allow for a magnetic toroidal moment. It can also occur in carbonyl magnets and in Rashba systems with warping. So we need the third order term in Rashba systems. In the same paper, today I concentrated on electrons, but all the effects we know can be transferred to magnons. And in the same paper, we predicted that there is also a spin-Nernst effect. So the Hall effect due to a temperature gradient is called Nernst effect. And there is also a magnetic spin Nernst effect. So this is the end of my talk. So I was allowed to talk until 5 minutes to 4. That was Jairo told me yesterday. And I'd like to thank you for your attention. And I'd like to mention collaborators.
So thank you, Ingrid, once again. Everybody raise their hands or to applaud. I guess that's the only thing we can do here in this webinar. As you can see, Ingrid, for the participants, everybody's raising their hands, so it's very nice. So now I'm going to ask a few quick questions around in 10 minutes. I have to leave and I will pass the hosting to Karen Evershaw. The first question was, and I think I maybe have also answered to in the chat, by Wei Davu, who doesn't want to be in the speaker because there's too much background noise. But I guess in the first part, when you talk about the topological Hall effect, you were in the exchange, in the large exchange limit, we assume, right? Where you have essentially a spinless model. Is that correct?
No, it's not really a spinless model. It's I was just considering just one block of band. I was in this limit that the band that I have full alignment of electron spins with the magnetic texture. And
that's what I mean by a spinless model, meaning that the spin that is anti-aligned is so far away that
and would give the same result.
It becomes an orbital effect, effectively.
Yeah, but it would give the same result with opposite sign.
Correct, yeah.
For this reason, I didn't discuss it. But we can calculate, of course, for all the other band structures where we don't have this extreme case, we can calculate it. It's not so clear. And of course, the topological, I mean, this quantized part is not so pronounced then.
Is what, sorry?
It's not so pronounced, since if I have overlap of all the bands, then I don't have so many gaps.
Exactly. They all clump together. That's the problem.
Yeah.
So let me, I think Igor has a question. So let me ask him to go ahead, Igor, if you had a
question. Okay. Hi. Thanks, Ingrid. Very interesting presentation. And I have a naive question. I'm not following the all literature on topological Hall effect, but I've been following some. And I did come across a statement that with spin orbit, you can have topological Hall effect in materials which have coplanar spins, so no scalar chirality. But I've never seen this very beautiful formulation that essentially you can transform out the spin orbit coupling, and as a result, you have effective canting. So basically, you create effective scalar chirality, and mathematically, the model can be reduced to non-relativistic Hamiltonian without with modified spin directions. So my question is that a property of this particular model that you consider, or you think it's a universal theorem which can be utilized with proper transformation in any sort of coplanar antiferromagnet?
I think it's so and so. It's of course a property of this model. And of course the model is kind of simplified. I think as soon, and we have one type of electrons in the model. I think as soon as you go to real systems and you have different types of electrons with different orbital character, you will have also different, you will never have one spin-orbit interaction, one constant lambda. For each type of electron, the lambda will be different. But I assume that in principle, each type of electron can be analyzed in this way. But then if you have different electrons in your system, you will get a superposition of all the contributions. And you could also imagine that you have different zeros in your angular dependence.
Yeah, okay. But as you presented, that looks like it just will be a more complicated transformation, but it still may exist. I mean, the transformation will be in the space.
I think, it may exist, but I think it was. This is our contribution, that in this, of course, simple model, you can show that there is a hidden symmetry in your Hamiltonian
Okay.
that is related to this virtual spin texture, and that makes the whole effect in the coplanar systems a little more transparent.
Okay, thank you.
So let me add a comment to that in terms of the transferability to the larger systems, and it's back to the topological Hall effect. The topological Hall effect has a very beautiful picture once you're in the large exchange limit, where the electrons are following the magnetization, and in here you have this, in this case, an atomistic level, this non-coplanar texture that you cannot really describe. You're not in that limit correctly exactly, because the distance between the electrons on the non-line up, the spins are close to the Fermi wavelength. But then this is where you can do the transformation on the spin-orbit coupling. If that energy scale of the exchange was reduced, then it would be a mess. You wouldn't have such a beautiful analogy. But in these materials, you really have that analogy. This is one of the beautiful things that paper that Ingrid did, that you, in those limits, but it works often. Similar to the topological Hall effect, it works quite often.
Yeah.
Harold, can I respond quickly to that?
Yeah, sure.
I think that's, I beg to distinguish between density functional formulation and many-body formulation. In many-body formulation, you need to have Hundrum's coupling, to have electrons aligned with local field all the time. In DFT or spin DFT, that's built in by definition, because you have effective potential, or effective magnetization, which changes direction from point to point, and by definition, your constant particle are always perfectly aligned with this.
Yeah.
That part.
So this would maybe I would like to comment on this. This is of course also an artifact of the model, that it's not a self-consistent treatment. So if you compare with DFT, you would self-consistently readjust your spin texture to